So, hi everyone, welcome back to Wired-In Software. This is my presentation about using sets and maps in configuration and measurement data. For those of you who don't know me, my name is Stuart Trevillian. I work for Wired-In Software here in Melbourne, Australia. Wired-In Software is owned by Chris Farmer, and he and I have been working together on and off for the last 24 years, having met him in the middle of the Australian outback, working on a defence project. If you've read my profile, you'll see that what I love doing is turning coffee into LabVIEW, and I've had plenty of practice doing that over 26 years. I started with about LabVIEW 4 or 5 back in the good old days when there were no projects, there was no undo function, and you would learn LabVIEW by reading books. Also, I have 3 kids, 2 dogs, 1 wife, and my favourite superhero is Batman. So, for my Giants of Female profile, I've chosen Professor Muthuni Musinde. She is a computer scientist, a meteorologist, and a mother of 4. And she is the creator of the ITiki drought prediction tool, which is currently being used in Kenya, Mozambique, and South Africa. Now, traditionally, farmers in her region would depend on observable indicators to determine when to plant or even what to plant, things like flowering trees or even the height that dragonflies are flying off the ground. But climate change has impacted that. So she has developed a system of wireless sensors placed on farms that measure rainfall and temperature and humidity. And in conjunction with local knowledge that's entered on the ITiki app by farmers, which they can enter using their mother tongue. So in conjunction with those scientific measurements from those remote stations, Professor Muthuni's models allow them to come up with predictions about rainfall and drought conditions to assist the farmers with planting their crops. So I found that to be a fantastic profile of a woman in technology in a challenging environment. So onto the presentation. I'm presenting on using maps and sets in configuration and measurement data. Now, this presentation is not designed as an introduction to maps and sets. It's more of a demonstration of the versatility of these and how we've applied them as solutions for a recent customer project. So I'm assuming a basic working knowledge of them here. If you need more of an introduction, maybe check out the presentations from Darren Nattinger or Alan Smith first, and there's plenty of other resources around to check out as well. I want to have a look at setting properties of front panel objects using maps, storing measurements in maps, and alarm stacks using sets. Just quickly about using collections, I found that I've been using maps and sets a lot more in my coding, where I used variant attributes before for lookup tables. I'm now using maps, and I'm able to migrate old code to maps reasonably easily. Maps allow you to define the data type, which is great during development. I was getting situations if I had multiple variants that I would wire the wrong variant to the wrong terminal. So the defined data types of the map stop that from happening now. And no more error 91 from trying to convert the wrong data type. That's a big one for me. Also, if you're not aware, you can use different data types for the keys, not just the values. You can see here that I've used Booleans as the keys for the top map and integers as the keys for the bottom map. And also there are, just I guess to note more than anything, there are no error terminals on the collection primitives, so that may have an impact on your sequencing or something. So for our previous customer project, the challenge that we were presented with was that we had a data monitoring application that utilised 2 data loggers that could be interchanged in hundreds of channels in different configurations for multiple test types. The one software package that we were developing had to deal with 2 different data loggers with their different module configurations and different channel counts and different channel configurations, 8 different test types that the customer needed, and customizable sensor setups. And the data loggers would only return their measurements by channel number. Then for each measurement cycle, we had multiple calculations to evaluate, such as airflow at standard temperature and pressure, and that used multiple measurement values and configurations. We wanted to highlight visually and any measurements that were out of limit. And also it would be nice not to display NAN if there was an invalid measurement, because not all operators know what that means. So we needed some method that would be able to handle all of these conditions. And we had to assume that for any given measurement type, it could come from any channel number on either of the data loggers. So our solution was to use maps to map channel numbers to channel names. And by using maps, measurements could be indexed by name and used for calculations and logging instead of having to repeatedly search through hundreds of array elements. All right, so let's have a look at this approach with a little demo. What I've set up here is a simulation of a data logger with only a handful of channels, not hundreds like in real life. This data logger has 10 channels, but we only have 3 sensors, pressure, temperature, and coffee count, on channels 101, 106, and 209. But those 3 sensors could be connected to any one of those data logger channels. And what we want to do is display the scaled and formatted measurements on each of these channels in the string indicators on the right-hand side and do limit checking on the measurements. If the measurement's out of limit, we will set the indicator to blinking. So on the left-hand side, I have a configuration that allows us to specify which sensors we have connected to which data logger channels and to set the properties of those signals. The properties in this case are the numerical limits, the display format, the units, and scaling. Maybe this configuration could come from an external file or a test configuration screen. So what we've done on the block diagram is we've used a map to store the properties for each of the string indicators. The data type for this map is a cluster that contains each of the channel properties that we defined in the table on the front panel, and also a reference to the front panel object itself. And what we do is we insert a key in the map for each of the string indicators. This for loop is running once for each of those indicators, where the indicator label is the key. So those labels are going to be pressure, temperature, and coffee in this case. And the values associated with those keys include the front panel reference, the configured data logger channel number, and all of those configured properties for those channel measurements that you saw on the front panel. So back on the front panel, if we display the map, you can see each of the properties in the config table is stored in the map, along with a reference to that string indicator. And also just note how the map sorts those keys alphabetically, not necessarily in the order that you set them on the block diagram. Awesome. So how are we going to use that? So the real data loggers are queried for their channel measurements every second, and they return a serial string containing all channel numbers and their unscaled measurements. So this loop simulates the acquisition cycle by returning a formatted data logger message every 1 second. And for every measurement that we're interested in, which is pressure and temperature and coffee, we index the map by the channel name and retrieve the front panel reference for the string indicator for that measurement. We know the channel number, so we extract the channel's measurement from the data logger message, and then we apply the other properties. So in this case, we scale the measurement and format it according to our format string. If it's an invalid number, we replace it with a dash instead of NaN, and then add the units on the end. And this is written to the value property of the string indicator. In parallel, we do a limit check on the scaled measurement and set the indicator to blinking if it's out of range. And I also found it useful to add a bit of sanity check information in the tip strip so that we can quickly check the settings, make sure that we're actually reading from the right or the expected channel. Now, of course, there's going to be a little bit of overhead here in using the property node to set the indicator value, as you're forcing LabVIEW to use the interface thread instead. But that's really just something to note if you're doing this thing repeatedly. So I think in the interests of time, I'm going to skip the demo. I'm just going to continue on through the slideshow. But what we found was that using this approach meant that we had a reconfigurable and scalable method of dealing with hundreds of input channels in any number of different configurations, and also meant that we could update the values and properties of any number of front panel indicators in a scalable way. And you can see how it's, I mean, it's just a screenshot, but it probably gives you an indication of how we're applying this and how it actually works. We can toggle those slides in the simulator. It modifies the data logger message, and then we're applying the scaling, we apply formatting, and we are doing limit checks on each of the indicators on the right-hand side there. And the top two indicators are in the middle of a blink in this screenshot. So yeah, we could have displayed the values in numerical indicators instead of in strings and use the display format to use units, to add the units, but we didn't want to be displaying NaN for invalid measurements, and that's why we use strings in this case. So if we extend the idea of channel indexed maps further, we stored the channel measurements in a separate map again, with the channel label again acting as the key. And we did this because we needed to use these measurements for the calculations that we needed to evaluate. If you remember, in real life, we have hundreds of channels, and we don't want to be searching through arrays of data each iteration to find the channel that we want. If the measurements can be stored in a map and then retrieved using the key, that saves a lot of development time. So let's say that we need to use the measurements for pressure, temperature, and coffee count to calculate two values, which I've called the coffee acceptance factor and the calorie count. Here we define a new map with just a single data type as the value to store the signal measurements, and we're going to use the channel names again as the key. So as the data logger signals are acquired, we add each to the map where the channel name is the key. And we can then use the key to retrieve the values for the channels that we need for our calculations. For our first calculation, we look in the map for pressure and coffee, and then multiply the values together to calculate the coffee acceptance factor. And we're going to do the same in the second calculation, except we're looking for all three measurements to calculate the total calorie count. And we all know that to calculate the total calorie count, we need to convert the coffee count to radians, subtract the reciprocal of the temperature, and multiply by the logarithm of the pressure, right? Everyone knows that.
Yeah.
And lastly, I just wanted to show how we're using sets as an alarm stack. So in our system, we might have several alarms from different independent sources. But say we want to centralize them into a single master alarm, which might be an indicator on the screen or an external light tower or a buzzer or something, so that if any one source alarm is active, then the output master alarm will be active. So sets can allow us to do that. If an input alarm is active, we can use insert into set. And if the alarm is cleared, then we use remove from set. But due to the nature of sets, if the alarm is already included in the set, then it won't add another instance of that alarm in the set or in the alarm stack. And this is particularly pertinent if you have a device driver that automatically tries to clear an alarm but keeps failing. So in the demo here, I've defined some different alarm conditions from different sources. I've coded this demo, excuse me, so that if the top alarm condition is set, it will continue to raise the same alarm every 1 second. The other alarms are just raised once. Now, the top alarm might be set if someone accidentally trips over the power cord for our power supply, and the device driver should raise an alarm, of course, when that happens. But if you program your drivers like me, you might try to automatically re-establish communication with the power supply at regular intervals, say every 1 second. So until someone plugs the power cord back in, the driver will continue raising the same alarm every second. So you can see in the alarm history on the right-hand side there, it shows the list of all the alarm occurrences that the code has received. But because we're using sets, every time we receive the alarm stack isn't getting any bigger because the alarm already exists. So I've set 2 alarm conditions here where the top one is recurring, but the current alarm list shows the 2 alarm codes and nothing more. In the code, we're checking this. In the code, we're checking the size of the set every loop, and if it's not empty, then we're setting the master alarm. And if we clear both alarm conditions, then the set will become empty and the master alarm will be cleared. In the case of the power supply, someone has plugged the power cord back in, the driver has then successfully re-established communication with the device, and the driver clears the alarm. It doesn't matter how many times the alarm was raised previously for the disconnected power supply, using the remove from set function will remove that alarm from the alarm stack. If one of the other alarms was still set, then it would appear on the alarm stack and the master alarm would remain set until it has been cleared as well. And that ends my presentation. Thanks for making it through this with me. I hope I've been able to help someone somewhere with using maps and sets in their LabVIEW coding. I think that there's a lot more use cases for using these functions that go beyond the simple introductory tutorials, and it could be quite fun figuring out how to utilize their functionality. So I'll leave it there. Unless there's any questions, we'll try and make this presentation and code available for download. And thank you again for listening. Yep. Question from the audience, Chris.
It's just actually a discussion I wanted to have with you. I think it'd be really cool to create an alarm kind of module, like a DQMH alarm module that we could build into our applications.
Yep.
And use that strategy to as a reusable module we can integrate into a lot of our applications.
So the comment is, if you weren't able to hear that, Chris is off to the side there, that it would be pretty cool to be able to reuse this alarm stack concept as a standalone DQMH module to be able to integrate into our future development. I'll take that as a comment. And, ask if there's any further questions. Are there any more, Michelle? No?
Yeah.
All right.
I think the hard thing is like just getting used to a new tool, right? You said at the start you used to use variant attributes a lot.
Yes.
And I just haven't gotten in my head around, hey, I can use maps and sets now.
Yes.
And I still revert back to what I did 6 years ago. So I think it's been good that you've been able to go to that next level and actually apply them.
Yes. Yes. So again, I'll take this as a comment. But yeah, Chris's feedback is that the use of sets and, sorry, how about you come over here and talk.
Hi, everyone. No, I was just saying that it's just really cool that you've been able to apply maps and sets. I'm still using the old ways, the variant attributes and things like that. So it just takes a bit of practice to actually leap over to the new tech. Yeah. Awesome work, Stuart. Thanks.
Excellent. All right. Well, I will leave it at that. We're close to the hour mark, and I hope everyone enjoys the summit.